And thank you to everybody for joining in today. I want to talk about vertical and horizontal panels, UHPC panels. And I always like to start with the reason I get out of bed every morning as a civil engineer. What is my mission in life? And as a civil engineer, planning, building, designing, maintaining, operating infrastructure is what it's all about. And it's what provides our quality of life. It's the clean water, food, sanitation, movement of goods, and the accommodation of people. And that's what excites me. And what better material to build sustainable, durable infrastructure for the next generation? UHPC. And that's why I get out of bed every morning, and I like to start with that purpose, and I hope it gets everybody else out of bed in the morning as well. So my presentation this morning, I want to talk a little bit about the key properties of UHPC. And I'm quite amazed that this is probably one of the first times that I've been on a panel or presentation where some of the previous speakers haven't explained what is UHPC. So up until now, today, nobody's really explained what is UHPC. And so I think that says something about our industry and the level of maturity we've come to, where people stop telling everybody what it is, because I would dare say that all of the people on this presentation know what UHPC is by now, and we don't have to keep telling them over and over and over. So, but I'm going to talk about the key properties. And then from there, I want to move into shape optimization of vertical and horizontal panels. And then I'm going to talk specifically about vertical horizontal panels, and then summarize some of the commonalities between the optimization process for both the vertical and horizontal panels. So I'm going to talk a little bit about properties, but not in terms of explaining what is UHPC, more about why these properties are important in the consideration of shape optimization. And I've broken this into four categories, what I consider four categories. One is compressive strength, and I show conventional versus UHPC. And then one is direct tensile strength. And as everybody knows, that's one of the key attributes of UHPC. It's a post-cracking, strain hardening tensile capacity. And I show a graph on the right of some dog bone prisms that were done in direct tension using the Swiss method. And then I want to talk about elastic modulus, because the elastic modulus is important, because the stiffer the material, the higher Young's modulus, the better it plays into serviceability in terms of deflection, vibration, et cetera. So you can see, it's about double normal concrete. And then I want to use permeability as a proxy for durability. Because the permeability, the low porosity, the disconnected pore structure is one of the key attributes of UHPC, which provides its durability, which leads to the improvement of all the other properties. So I use permeability as a proxy in terms of representing durability. And you can see here that the permeability is 2 orders of magnitude better than normal concrete. It's 1 order of magnitude better than high performance concrete. So high performance concrete falls in the middle between conventional and UHPC. So without getting into any more about what is UHPC, I want to talk about how these, what I call key important properties, are used and how they drive the optimization process for UHPC. So I put together here a little chart showing the 4 properties: the compressive strength, the tensile strength, Young's modulus, and my proxy for durability, and how it impacts the attributes when we're looking at the optimization of UHPC. So all 4 of these properties contribute to a thinner section. And of course, when you have a thinner section, you also have a reduced dead load. So all 4 of these also contribute to reduced dead load. The strength properties allow us to go with longer spans, so you can have longer span in the structures. You can eliminate rebar because of the post-cracking tensile properties of the UHPC. You can either reduce or eliminate depending on the type of application and what you're trying to design. And the tensile properties also improve the crack control because of the fibers. You can reduce the amount of cover on any embedded reinforcing by both the tensile properties and the durability properties allow you to reduce cover. And I talked about reduced dead load already. All four of the properties are also contributing to the ability to do complex shapes that are thinner, shapes that are curved, complex in terms of shaping, also perforated panels, etc. So all four of them contribute to that, and all four of them contribute to the aesthetics. So that sort of summarizes the levers that we have in terms of shape optimization. So what I've done is I've taken those levers, and I've looked at how different materials use their mechanical properties or their building mechanical properties to design an element. And so, for example, in steel, what you find is you're doing a steel deck. It's a corrugated steel deck, because if you do a flat plate steel deck, you have large deflections because a thin plate spanning between two supports will have a large deflection. So they use corrugated metal deck, and that spans between a couple of girders or beams. We put some rebar in the corrugations, and we put some concrete on top. So a steel deck looks typically like this. The steel wall panel, very similar. You have a thin plate. You have some purlins and beams, two directions to stiffen it up. This may be 2 layers of steel with some insulation in between if it's an insulated steel panel. So again, you see a thin plate with some stiffeners in both directions. Concrete is a more massive material, and so typically we have a concrete slab with some reinforcing steel spanning between some beams. And similarly on a wall panel, we'll have 1 or 2 layers of rebar, a panel that's spanning between connections in a structure. So when we go to UHPC, because of the higher strength properties, we find that it performs more like steel. However, it is not as strong in tension as steel. So when we start optimizing the shapes for UHPC, we find that we can go with a much thinner section compared to normal concrete. But when you go with thinner section, you get the same problem you have with steel. You have high deflections, so consequently you need to stiffen it. So rather than thicken the structure for stiffness, we add ribs, 1 or 2 way. So you end up with a waffle deck type solution. And we can put some rebar in the ribs, top and bottom. And so you end up with this type of a section for a deck. And when we go to wall panels, what I've shown here is a insulated wall panel. So you can have a layer of insulation in between 2 widths of material, again with ribs to stiffen for deflection. And if you put this panel into load bearing, you want to make sure that you don't get too much buckling and bowing, because then you get eccentricities which amplify the bending moment in the panel. So you end up with this type of a shape profile to stiffen the thin panel skins on a wall panel. So that's the type of optimizations that these kind of mechanical properties tend to drive. So I want to look at very specifically some applications of vertical and horizontal panels. And I show a suspension bridge here, and I raise the question, waffle deck panels on a suspension bridge. I'm going to leave that question. I'm not going to answer it until we get back to the end. We'll circle back. But today in North America, there's about 45 suspension bridges that are more than 50 years old. Half of those are pre-World War II, and then half of them are post-World War II, which a lot of them were built in the Eisenhower interstate system time. The average age of these 45 bridges is somewhere in the range of 80 to 85 years old. So you can see that there's a large opportunity in suspension bridges for UHPC. Because suspension bridges flex, there's a lot of torsion, a lot of movement due to wind and truck traffic because they're quite flexible. They need a deck that has some flexibility, some ductility. And so UHPC is a good solution. And so we'll take a look and we'll circle back on this as we come towards the end of the presentation. So I want to first start with load-bearing insulated UHP sandwich panels. So this particular application, we're working with Queen's University and the Canadian Precast Concrete Institute and producing, it's a 1-inch thick skin with some ribs, using a minimum of 18,000 PSI compressive strength UHPC, 6 inches of insulation, and we're using glass fiber GFRP bars as the connectors to connect the panels together. The overall panel is about 8 inches in thickness, and this is what it looks like. And so here you can see the 1 inch of UHPC with a rib, and you can put a pre-stressing strand or rebar in the rib. When we do these on a long bed, we put a pre-stressing strand, and you can saw cut through the panel to customize the length. So this is an application that's been being researched and is starting to go into production. We're working with a couple of precasters right now and trying to implement this system. And here you can see in the bottom right, this is a panel without any ribs. So this is 2 wides, 1 inch thick, with the insulation in between. There is no ribs on this panel, and you can see the amount of ductility, flexibility in this particular panel. But in a wall panel, you don't want this type of deflection because it will amplify, the axial loads will amplify the bending moment and creates more problem in the structural design. So you need more stiffness in order to avoid this kind of deflection. So this was the first round of testing without ribs, and then the ribs were implemented in the second round of testing to improve the stiffness of the structure. So this is work that was done at Queen's University with CPCI. So some of the applications of this, there's a lot of industrial buildings, warehousing, storage buildings, recreational centers, shopping malls. They use these concrete panels with insulated sandwich panels. Very common in the northern climate. And with the change in the energy codes that are coming in right now in Canada and around the world, we see the requirements for more and more insulation. So with conventional concrete, these panels are already 13 inches thick, and as they add more insulation to meet the energy code, they're becoming very bulky and thick. And so UHPC is a logical way to reduce the mass of the panels, reduce the shipping costs, and actually increase the height of the panels at the same time. So it is a big potential market. There's a very large market in this area, and as I mentioned, we're working with a couple of precasters now to supply this product into the market. So I want to talk about horizontal panels, waffle deck panels. So the waffle deck panel is typically precast on approximately an 8-foot grid with panels that are 2 by 2, ribs in 2 directions. So if you design a UHPC slab to span between 2 beams, you may only need 4 inches or more or less of material, but you end up with high deflections. You end up with a flexible deck that does not give very good load distribution across adjacent girders. So you need a stiffer deck to improve load sharing, reduce deflections on the bridge. So you end up with using a waffle deck, which reduces the quantity of material. So these decks are about 2.5 inches thick, 5.5 inch deep ribs. So the overall thickness is 8 inches, which is very similar to what you currently have in a bridge deck anyway. So if you go into retrofit an existing bridge, you tear off the deck, putting in an 8-inch deck, when you take off a more or less an 8-inch deck, manages the profile quite nicely. And also it ends up with a deck that's stiff enough to do some load distribution and minimize deflections between the girders. So we put some rebar in the ribs in both directions, project the rebar out into the connection between the adjacent panels, and then we fill that connection with UHPC. So you have 100% UHPC connection. And this panel spans from the center girder. So on the left here would be where the center is, and that's typically where your crown is in the road. It would slope down, cross over 2 girders in this particular panel. And then this one shows 2-panel cantilever, but typically it's 1 panel. And that outside panel can be solid to receive the barrier on the outside of the bridge. Over the girder, you see here a bar coming out of the beam, fill the UHPC connection, and you end up with a horizontal shear connection to the girder.
Vic, you have 1 minute.
Thank you. So here's an example of the project. This project was done in Wapello County, Iowa. You see the girder centerline span going across and the underside of the girder. So I'm going to go quickly through here. The steel form, perimeter form, top form and we put the texture on the bottom of the form. And if we're doing a mock-up, we can use wood forms. The previous ones were steel. So here you see wood forms perimeter and a wood form on the top form with the rebar already in place. So you cast the UHPC, batch it up in the mixer, put a fixed volume in because you know the volume for the panel. So you fill up the form with the fixed quantity of material. And on the larger panel, use a trough form to get better fiber distribution going from one end to the other. And then we put the displacement form in. So on the mock-up, it's a wooden one, push it down into the material and extrudes up and forms the ribs, displaces the material. And similarly in the production one, with the steel form. And then once the material starts to set, you can release that internal form to remove any restraint during shrinkage and during curing before the material gains its tensile strength. Once it's cured, you can flip it over on a rotating table, or you can pick up a small panel using slings on the bars. Here we see the panels ready for shipping, and I showed the interface at the edge of the panel where we're going to cast the UHPC connection up against the UHPC panel. It actually bonds very well, UHPC to UHPC. So here's the finished bridge ready for traffic. And on the right, we're doing some water testing on the connections. I always like to go back and check the project after a period of time to see how it's performing, and doing a water test on the connections is always interesting. So some of the commonalities between these panels are thin to reduce the quantity of material and weight, but they need to be stiffened with 1 or 2-way ribs for serviceability requirements and to facilitate the connection of the thin panel to the structure. We eliminate a lot of the passive reinforcing, and they're typically long, slender units. So can we use waffle deck panels in suspension bridges? Yes, I believe we can, and I believe there's a big opportunity going forward. And we will be promoting this concept to the owners of suspension bridges as we go forward. So I want to end with my challenge to everybody. Open your mind and consider all the opportunities where you can use vertical and horizontal 1 and 2-way ribbed UHPC panels. The infrastructure world is your oyster. Go harvest.